Alright guys, here we go. Buenos dias. Today's Cinco de Mayo, no, Uno de Mayo, first day of May. We've broken up section 11.2 into two parts. This first part, yesterday's part was just a basic kind of understanding of central angles and arc measures. Kind of a new concept. It's sort of a straightforward concept. Hopefully the homework was easy last night. I think this is a little step up from what we did yesterday. It relies on knowing what you did yesterday as knowledge. So, first thing to sort of dive into here, I've got these three polygons. They're not just regular old polygons, they're regular polygons. And regular meaning the geometry word for regular, meaning that the angles are all congruent and the sides are congruent. And they've been drawn inside of a circle so that each vertex touches a circle. There's a vocab word for that, which you should be able to write down here. It's the opposite of circumscribed. You could say the circle is circumscribed about the polygon. You could say the polygon is inscribed within the circle. And I'm using this sort of simple model here to sort of derive or intuitively come up with a theorem in a minute here. So intuitively find the measure of each arc. In other words, this pentagon, 1, 2, 3, 4, 5, has been inscribed inside this circle. Figure out the measure of all 5 of these arcs. And usually if I'm in class on this day, I kind of pause. I've got my clock up here to remind myself to just pause and let people think for a minute and kind of do it on their own without any instruction whatsoever. If you know what the word regular means, meaning that all sides are equal, all sides are congruent, this is a pretty simple concept. You know, the fact that all these chords, all these sides of the polygons are equal, makes it easy to find all of these 8 arcs that are around this octagon. And the same thing for the hexagon on the right-hand side. 1, 2, 3, 4, 5, 6 sides. It means that all of these arcs are pretty intuitive to find. So it's a good time to pause or just kind of work on your own here. Find the measure of all 6 arcs around the circle. It could take you 10 seconds for this one. The other two, the numbers are a little trickier to work with maybe. Maybe you don't want to do mental math, maybe pull out a calculator. Again, a good time to pause. I think you should come up with 60 for the hexagon. For all of them. And of course that makes sense from yesterday. We talked about what these would add up to for a circle. They add up to 360. And it's probably logical that if there's 6 of them, if these sides are equal, it kind of just makes sense that they would equally cut the circle into 6 parts. Not very hard. For the pentagon, think about how you find all 5 of these. You know they add up to 360. It just sort of makes sense that these would logically be equal to each other because the polygon, the pentagon were all equal, sides were all equal. 360 divided by 5 gets you 72. And of course if you took 72 plus 72 plus 72 plus 72 plus 72, you'd get 360. Same idea with the octagon. Should be an easy one. Take 360 divided by 8 and you get 45 for all of them. So I'm hoping that's very simple. It's supposed to be intuitive. Not a lot of instruction needed for that. We've basically just discovered, kind of indirectly, this theorem here that says if you have congruent, and of course the first thing I marked was congruent chords, those congruent chords basically cut the circle into congruent arcs. In other words, if these are equal in length, that the curved part would be equal in length and also equal in angle measure. So that's the first theorem. We got 2 theorems today. We'll cover them both in the front, and then we'll do some examples on the back here. Congruent arcs theorem, very, very simple. I'll give you a minute to draw these, sketch, and maybe use a ruler to sketch these. Try to be accurate here. These 2 chords have to be equal. Just like on the previous problems, I had regular polygons where the side lengths were equal. They don't have to make a polygon, but I just need to get 2 chords that are equal in length. I don't care how long you make them. Don't make them too small because you want to be able to draw on this in a minute. And basically this theorem says what we just kind of discovered there. If these arcs are congruent, so if this arc is congruent to that arc, these chords would have to also be congruent. And the logic of this, because it says if and only if, works sort of forwards and backwards. In other words, if the chords are congruent, the arcs are congruent. If arcs are congruent, then these lengths would have to be congruent. And we sort of just figured out why it makes sense in the previous one. Now we'll prove it. And the proof is only like a 3-step proof. I'm already giving you the givens. You don't have to restate them. We do want to end with arc x and y. And by x and y, I mean the 2 intercepted arcs that are connected with these chords. Prove that x and y are equal. with the given being that this chord is equal in length to that chord. It says there's another given here. It's not really a given, but you're going to have to draw 4 radii to get this. And it's obvious that radii are congruent because it's only one circle on there. So some of you could probably do this on your own, but I'll give you the prompt for it. If you draw these 2 radii, you now have a triangle. And we spent a heck of a lot of time proving that 2 triangles are congruent. So I'm going to draw 2 more radii here. It's pretty darn obvious that this side is equal to this side is equal to this side is equal to this side because of the radii. So it would therefore be pretty easy to prove this triangle is congruent to that triangle. That's the main step in this proof. Prove the triangles are congruent. Now I want to connect this with something you did yesterday. You knew from yesterday if this arc was x degrees, this angle here at the center was also x degrees. And if this arc is y degrees, the central angle is also y degrees. That's going to be a part of our proof as well. You know, if we want to prove the arcs are congruent, we can do it by proving that these 2 angles are congruent. And if we want to prove the angles are congruent, we can do it by proving the triangles themselves are congruent. So like I said, it's 3 steps, pretty quick. Prove that triangle X, and by that I mean the top triangle, is congruent to triangle Y. I've started using informal language on here. The top triangle and the bottom triangle are congruent. You know, what's your reason why? Well, duh. You got radii that are congruent. You got a chord that's congruent. You basically have 3 pairs of sides that are congruent. So side, side, side. And think back to what you do after you prove sides are congruent. What do you often do in the triangle congruence chapter, the triangle congruence study? Well, you use CP/CTC to prove the parts are congruent. If this triangle is congruent to that triangle, then of course this angle is equal to that angle. So angle X and angle Y. I'm sort of doing this informal language again, but the 2 angles are congruent because they are congruent parts of the 2 congruent triangles. And then, you know, the last step of this is, well, duh, if this is congruent to this, then of course this is congruent to this. The arcs are congruent. Arc X and arc Y. Again, this is not good language here. We've been using 2 letters or 3 letters to describe arcs. I'm just trying to make the proof of this kind of quick. Quick and logical. We're in and out. We move on to some actual problems here. And of course, this is true because they are associated with the central angles. You know, we said yesterday an arc is equal to a central angle, and this arc is equal to that central angle. This arc is equal to that central angle, so it sort of just makes sense. It's sort of a definition, sort of a theorem that deals with central angles and arcs. All right, we'll dive into the second one in part 2, second theorem in part 2.